Hi, I'm Karl Riley, president of ELF Magnetic Surveys and the author of the book Tracing EMFs in Building Wiring and Grounding. In 1997 and 98, the California Department of Health Services hired an electrical engineering firm to randomly survey 90 schools statewide in order to measure the electric and magnetic fields from electrical power sources. The engineers made a surprising discovery. Most of the elevated fields were not due to external sources, but wiring within the building. My job in the California school study was to lead the team that identified the sources of elevated magnetic fields in the building wiring. The main error we found was the improper connection of neutrals and grounds. This type of error can cause arcing, heating of circuits, and premature aging of the insulation. This in turn increases the risk of fire. The study provided data which suggests that as many as 40% of schools have at least one miswired circuit creating elevated magnetic fields. With the assistance of Mark Chapman, journeyman electrician, we'll show you how in the course of routine work on your school's electrical system, you can determine if there are misconnected neutrals in the building wiring. We'll also show you how to correct those problems. But first, let's answer some basic questions. There is both a theoretical and practical definition of a net current. In this video, we will use the word neutral to refer to the grounded circuit conductor by common usage. When a wire conducts current, a magnetic field is created around the wire. The strength of the field is proportional to the amount of current, or amps, flowing through the wire. In this example, the hot leg carries 10 amps. In a normal circuit, the neutral leg also carries 10 amps. The net current here is 0, because both legs conduct the same amount of current, but in opposite directions. Now let's measure an actual circuit. Here we have a simple circuit. We clamp our ammeter around the zip cord and see 0 amps net current. Now if we place a Gauss meter probe 6 inches away from the conductors, we will read 0.3 of a milligauss. A milligauss is a unit of measure for magnetic fields. To check the current, we split the zip cord and measure the hot and the neutral separately. The hot measures 1.4 amps, and the neutral the same. This is a normal situation. A net current is created when there is unequal current flowing through wires. For example, if the hot leg carries 5 amps and the neutral carries 2 amps, the net current is 3 amps. This 3 amp net current produces the same magnetic field as if 3 amps flowed in a single conductor. But how are we going to get an unequal amount of current in the return neutral? Let's look at a diagram of a circuit where an extra neutral has been added in parallel with the first. The neutral return current now has 2 paths, and the current divides in accordance with the relative impedance of each path. In this graphic, we've assumed a higher impedance in the second path. The net current is 5 amps from both parts of the circuit. 12 minus 7 equals 5. When neutral current is shunted, the net currents on both paths will be the same. Now let's see if our measurements verify the theory. We've added a parallel neutral, but kept the load the same. The hot still measures 1.2 amps. The dedicated neutral now measures 0.9 amps. Clamping around both, the net current is 0.3 amps. We see that the net current is the remainder of the neutral subtracted from the hot. We would now expect to see the missing 0.3 of an amp on the parallel neutral. We measure 0.3 of an amp. Now let's see what splitting the neutral current does to the magnetic field. Before paralleling, our Gauss meter measured 0.2 of a milligauss at 6 inches from the cord. Now it measures 1.9 milligauss. Now if we put the Gauss meter probe inside the loop and move it across the loop, we note that the field maintains a high and fairly constant level. Inside a school, a series of classrooms could be enclosed by such a loop. The most common cause of this situation is neutral-to-neutral shunting, especially in situations where two branched circuits share a junction box. This illustration shows a typical wiring configuration in which a wiring error can produce a pair of net currents. There are two branch circuits, number 1 and number 2, supplying their separate loads. At one point, they share a junction box. This should not be a problem. The question is, how are neutrals in that shared junction box connected? The fact is, the misconnection of neutrals is the most common cause of elevated magnetic fields in school buildings today. Understanding why this happens and what to do to correct the problem is the single most important thing you can do to eliminate wiring errors and reduce EMFs. Here we see an example of an incorrectly wired junction box in which neutrals from two branch circuits are joined. This wire nut connection allows the neutral from either load to run in both circuits in parallel paths in different cables or conduits. In this situation, when the neutral return current from either load reaches the wire nut, instead of going back with its corresponding hot, it splits and goes back on both circuits. This connection violates both National Electrical Code sections 300-3B and 310-4. Section 300-3B states that all conductors of the same circuit and, where used, the grounded conductor and all equipment grounding conductors shall be contained within the same raceway, auxiliary gutter, cable tray, trench, cable, or cord. Section 310-4 does not allow conductors to be paralleled, that is, joined at both ends, unless they are size 1/0 or larger. So you can't join two neutrals at a junction box when they're also joined at the panel bus. But why does the NEC make this a code violation? Is it just some bureaucratic requirement? Not at all. When you allow some of the current in a circuit to travel in alternate paths, you cause magnetic fields to spread out from both conducting paths. These oscillating fields induce currents in any nearby conductors, and particularly conduits. This leads to heating, so that the temperature in the conduit exceeds its rating and the insulation on the conductors begins to deteriorate. Premature aging can lead to fire. Secondly, there is a shock danger when neutrals of two circuits are paralleled. When an electrician opens a breaker to work on a circuit, he expects that circuit to be dead. But the neutral will be live, as he will see by the spark when he disconnects it, hopefully with an insulated tool. Now, the obvious question at this point is, how should the neutrals in that junction box have been connected? The answer is to use two wire nuts instead of one. Connect the load neutral to its own supply neutral and not to the other branch circuit neutral. Here is how the correct wiring looks inside a junction box serving one branch circuit. In most junction boxes, all neutrals may be joined since only one branch circuit feeds all loads. Now, there's nothing wrong with using one wire nut to connect all neutrals in a junction box when there's only one branch circuit present. It is only when a junction box is shared by two branch circuit feeds that you must keep the neutrals from each circuit separate. In this junction box, the neutrals from three loads are connected to the returning neutral. There is no splitting of the return current and no net current. So far, we've seen only one example of how to misconnect neutrals, but there are several other ways to go wrong. Here are some examples. In this example, the hot comes from one circuit and the neutral goes back on another. The net current equals the full load. Everyone knows not to do this, but we do see this error at times. In this example, the neutrals are mixed up. When the wrong neutrals run with the circuit, there will be net currents. The installer did not pay attention to which neutrals he was connecting, but since the lights came on, no one noticed. And in a situation where one hot leg has been paired with a neutral of the other hot leg, the result is that instead of subtracting from the hot, the neutral will add to the hot, producing a high net current. Another situation which violates the National Electrical Code is one in which neutral to ground connections are made on the load side of the service entrance point, which means anywhere inside the building past the main disconnect switch. Section 250-24A5 does not allow this connection. There are real dangers involved in connecting neutral to ground within a building. See your written protocol for a fuller explanation. The 1993 NEC Handbook points out the possibility of arcing in concealed spaces leading to fire and the shock potential to workers. When a neutral is connected to the grounding conductors, it will travel in all available metallic pathways which lead back towards the service entrance point. This creates a situation in which there are multiple net current sources creating magnetic fields throughout the building. The green paths shown here are carrying neutral current in parallel with the neutral conductor due to a neutral ground connection in the circuit. Now let's look at how these connections come about. There are three fundamental ways neutral gets on grounding conductors. We'll illustrate the main one on our demonstration subpanel. The first is when a neutral bus is bonded to the subpanel, or there are equipment grounds connected to the neutral bus. Here we're using a simplified demonstration panel to illustrate various misconnections. The consequences of this situation are currents on various metallic structures in the building, as well as a net current on the panel feed all the way back to the service entrance point. The neutral bus must remain insulated from the panel and the bonding screw either turned out or removed. It's only there in case the panel were to be used as service entrance equipment. Also, check to see that no neutral is connected to the grounding bus. Sometimes a neutral to ground error is found out in the circuit. Here is an example of such an error. The neutral is grounded because the neutral wire is nicked. Sometimes the sharp edges of a fluorescent light fixture mounted without the correct bushings will cut through the neutral insulation. And a third situation involves an intentional neutral connection to a grounding conductor. This happens for various reasons. Some electricians may not understand why neutrals must be isolated from ground until reaching the service entrance point. Others may not be familiar with the code. An attitude sometimes expressed is, since neutral is bonded to ground at the service panel, why not here too? Hopefully, this video is explaining why not, fire and shock hazard, as well as interference with electronic equipment, such as computer monitors. Let's look at another common source of area magnetic fields, created this time by miswired three-way switch circuits. First, we see a diagram of one correct way to wire a three-way switch circuit. As expected, the hot and neutral feed into switch 1. As you follow the paths of hot and neutral currents, note that at every run, there are two equal and opposite currents balancing each other out. Note that the traveler must have three conductors. Now let's look at one of the many ways to miswire a three-way circuit. The installer uses only the hot to run to switch 1. This enables him to use a two-conductor traveler to switch 2, since he picks up a neutral from a circuit near switch 2. The result is net current and high magnetic fields from every part of these circuits except the run to the light. This installation violates NEC 300-3B. There is no way to get by with using a two-conductor traveler. Since three-way switch errors may occur in only one portion of the circuit, they may not be detectable at the panel. A Gauss meter will detect the net current portion of the circuit, or a clamp-on ammeter around the conduits will trace it. Okay, now that you're familiar with what net currents are and what causes them, let's take a look at the various ways to trace and correct wiring errors. You start with the breaker subpanel, which serves the area with the net current magnetic fields. Here is a cautionary note. Removing the cover from a breaker panel while the breaker panel is energized exposes voltage-carrying uninsulated parts. Only qualified electrical personnel should perform this work, and such personnel should always use the proper safety precautions. After removing the breaker panel cover, perform a visual check. Ask yourself the following questions. Is the neutral bus insulated from the box as it should be? Is there a prohibited bond? Is the bonding screw in or out? It should be out. Are any equipment grounds connected to the neutral bus? They should have their own bus or connectors. Are any neutrals connected to a grounding bus? As you can see, we've put all these errors into this panel. Now we begin the net current search. First, check the panel feed conductors for net current using a large-jawed clamp-on ammeter. If there is a net current, record it.
4 amps.
Now we want to know, is this net current due to missing neutral current? First, clamp around the hots and record.
16 amps.
Then clamp around the neutral and record.
8 amps.
If there is an equipment grounding conductor, clamp around and record.
4 amps.
The current on the hots should equal the current on the neutral. There should be no current on the ground. If some neutral current is missing, suspect a neutral to ground connection in the panel or in one of the circuits. If there is too much neutral current, suspect a shared neutral with a circuit from another panel. Next, we want to identify any circuits carrying net current. The method is basically simple. We clamp an ammeter around each group of conductors leaving the box. If the ammeter reads 0, no problem. If it reads more than a couple of tenths of an amp, we investigate further. But to perform a simple procedure such as this may be impossible if your clamp-on ammeter is the wrong size. So let's take a moment to check our tools. This mini clamp-on is very easy to use and will get around small groups of conductors as well as around small conduits. See your handout for details on all these meters. Also very useful is this inexpensive probe with thin jaws for larger conductors and conduits, and some water pipes. It plugs into a digital multimeter with an AC millivolt setting. 1 millivolt equals 1 amp. This one, made by Fluke, has a min-max and averaging function, which is useful if you're measuring a fluctuating current. For large service conductor cables, bus ducts, and large water pipes, there's nothing like a 2-foot or 3-foot flexible probe. The unit plugs into a digital multimeter. Here are 2 such units. To show you what Gauss meters look like, here are 3 examples. 2 triaxial models, one for area surveys and one for data logging. And here is a single-axis probe and meter for troubleshooting. For more information on Gauss meters, see your handout. To resume our search for net current circuits, you will need to clamp around each group from every conduit and record your measurements. You can find a suggested form in your handout. To obtain the measurements, clamp around each group. Sometimes it is easier to clamp around the conduits outside the box. Once you've found a conduit group with net current, you can trace it out into the building. If you want to know what is causing the net current situation, you can measure the hots and neutrals in the panel box. Your next step is to trace the net current circuits to the location of the error. If you have an idea where the error may be found based on your panel investigation, go to it. If not, follow this procedure. You will usually be working in the ceiling. To show the tracing technique, we will use this live model. Using your clamp-on, follow the conduit with the net current to the first junction box. Note which conduits carry the net current. Open it if you need to understand the connections inside. Otherwise, keep going. Watch the meter display as our electrician clamps onto the conduits. Follow the conduits with net current. Here we see that the net current leads us to a box with 4 conduits. Usually, the box you're looking for has at least 4 conduits. Open the box. Here we see that the neutrals from 2 branch circuits have been connected together. We have found the source of the net currents. Now open the breakers for these 2 circuits to de-energize and correct the error. Now energize the circuit and check the conduits again. No net current. Your school may want you to verify that the previously measured magnetic field levels have decreased. Refer to the original area magnetic field measurements and remeasure with the Gauss meter. If you follow this process, you will clear the magnetic fields in the building. It's detective work, and there is a certain suspense until you find the error. But the moment you correct it, the field disappears. So, good hunting.